Today we're going to start section 1.1, which is mathematics and problem solving. And this is a really good example page of why you want to have your notes printed out, because there's a whole bunch of writing that you don't have to do if they're printed out, right? So there's a four-step problem solving process. Whether we complete every single step like on paper, they're good steps to keep in mind as we're trying to solve problems. So the first step is to simply understand what the problem's asking you to do. Understand the problem. And these are some kind of questions to think about as you're sort of processing, do I understand this problem? Sometimes we think of them in different situations more often than others. Like one of these might be more prevalently used. So can I state the problem differently? What is it I'm trying to find? What are the things I don't know? What information can I find already given to me in this problem? And what is either not needed or maybe is missing? So in particular, in real life, there's often a lot of things that are not needed or that are missing when you're trying to solve a problem. So that's a very vital step for real life kind of stuff. After you've sort of parsed through what it is you're trying to find, figured out what it is you know and don't know in a particular problem, you're trying to figure out how am I going to solve it? What are my options? So you're going to devise a plan. The following is a non-exhaustive list of strategies. That means this isn't all the strategies there are, but these are just some problem-solving strategies that are often useful. Look for a pattern, right? The whole last year and a half has been about patterns. You see people talking about, COVID numbers going up and down based on what the expectations are in other countries or in other areas, or based on the last time it went up and down. So patterns is a really big thing. Examine related problems, right? Look for something else that's similar to the problem you're trying to approach and see if you can utilize that strategy. Look for a simpler or a special case. So if you're trying to consider, there's an example we're going to do later. I'm going to expand it a little bit. Like, let's say you were in a position where you were trying to organize something that had 100 people with it, and you're trying to figure out how to organize it in a productive way. Well, it might be easier to think, well, what if I didn't have 100 people? What if it were just 10? And if I can figure out a way to do it with 10 people, maybe I can expand that idea to 100 people. Okay, looking for something smaller. Tables and lists. How many of you are list makers? Yep, there's one in my office right now. I just want to mark the things off the list. It's a big deal for me. Organizing things in lists is also sometimes helpful depending on how your brain works. Lists are really helpful for me to organize when I'm trying to think through a problem. Identify a sub-goal. Sometimes you can think, I can break this down into steps. If I can get to this point, then I'll know how to finish it. Or, if I think I can get to this point, and then I'll have to figure out what to do next. So, an intermediate goal along the way. Diagrams, we're going to do an example with a diagram. Even if you're not a good artist, sometimes a picture can help you to solve something if it's got geometric implication to it. So diagrams are often helpful. Guess and check is actually not a bad strategy sometimes. Doing it just sort of random, haphazard is probably not your best plan. But with some kind of a structure behind it, guess and check can be very useful. Working backwards. So working backwards is something you've all done when you've looked at the back of the book answer and said, how'd they get that, right? But sometimes there are problems that lend themselves to working backward really well, and we'll see an example of that one. The last one actually says write an equation, and while there's nothing wrong with that, this particular course that you guys are in is really not that. So if you found and did it with an equation, I'm not going to be upset about it, but the reality is this class is supposed to be sort of the elementary math that would go through maybe 3rd, 4th grade. And they're not doing a whole lot of equations by 3rd and 4th grade. So that's not really where we're trying to think of when we're trying to solve these problems, is this equation perspective. Again, if you did it that way, I'm not going to be mad at you, but I'm not going to teach it that way, okay? Next one is to follow or to carry out the plan. What did you decide to do? Now what are you going to do with that? So take the strategy you chose and then start working with it. Pay attention to the language that's being used. Check the steps along the way, either formally. So formally means like you're just really checking to make sure that math that you just did, that multiplication or that addition, was correct. Or informally, which says, does that seem reasonable? Right? Somehow my calculator gave me an answer that I wasn't quite expecting. It doesn't sound quite right. So now I've got to figure out what happened wrong. So that's informal checking or intuitively checking. Keep an accurate record of your work. If you don't keep a record of your work and you do find that there's an error or you know something's wrong, just like it's not correct, it's really hard to then figure out what you did wrong along the way if you haven't kept any record of it. It means you really have to go back to square one. And that always stinks. Nobody likes to start over. And the last thing along the way is to decide, to check your work, to decide if your answer is reasonable. Okay, so that's what I was just talking about before too, right? Does that make sense? Is that possible? When I was a grad student, we had a test where every now and then there was a question where students would get the wrong answer, and the wrong answer would tell them something like it was 42.73 termites. You can't have a 0.73 of a termite, right? That doesn't make sense. There's something wrong with the math along the way that yielded that answer. And then check the accuracy. So accuracy means, like, is it actually, like, the numbers that you multiplied them out or added them together, whatever, did you do that correctly? Okay, so we have time for one problem, and this is a very interesting one. Our gentleman that is, he's a mathematician, his name is Gauss. When Gauss, who's a very bright, intelligent child, okay, and he was very prolific in terms of proving things and working in mathematics later. When he was a child in early grade school, his teacher gave the class an assignment. It was supposed to take them a lot of time, right? Busy work is what it really was. She wanted them to add the numbers from 1 to 100, okay? So as you can imagine, most children would say 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, right? And they just would go up from there, right? That would take a while. Agreed? Okay. Gauss answered almost immediately. So what he did is he actually noticed quickly a pattern. So I'm going to show you his method to thinking about the addition of multiple numbers, and then we're going to look next time at how to extend his idea to similar questions. So what Gauss did is he sort of thought about, and we're going to write down, give yourself some space before it and after it. So we're just going to write down 1, 2, 3, and then we're going to leave a space, and we're going to write down the last three numbers, which would be 98, 99. I meant to put addition between there, not a comma, sorry. And 100. And just for a little structure, because we're going to be working on it together, I'm going to give this a name, and I'm just going to call this sum S. So whatever this is, it's S, if I add these things all together. What he noticed is what I'm about to show you, is that if you flip the numbers around, like this, and you add them together, something very interesting happens. So we're just going to start with the first one. 1 plus 100 is 101. 2 plus 99 is 101. 3 plus 98 is 101. And in fact, they all are, right? So I'm not even going to write all of them out at the end, but they're all 101s. We've got a whole bunch of 101s added together. And the reality is that it's a lot easier to add the same number together multiple times than different numbers. So he took something and he made it kind of easier by noticing there was a pattern involved. Now in doing so, this is now twice as much as we had before. So I'm going to call it 2s, just reminding yourselves that it's twice the sum, right? I had the sum before, whatever it was, and now I have twice that because I added it to itself. Is everybody good so far? Okay. So how many of these are there? There are 100 of them. Start at 1, I end at 100, that's 100 numbers. We will explore next time what happens if we don't start at 1 and we don't have every single number and we don't end at 100. Like what happens when we change that up a little bit. But for this one, it's 100 numbers. So how can I figure out what 101 is added together 100 times? Multiply. You're right. So this is 100 101s added together. So what's 100 times 101? Yeah, because the number's so nice, right? A child might be able to pull that off. It's 10,100. Right, because you just put zeros on when you multiply by powers of 10. So if twice the sum is 10,100, what's my sum? Yeah, I'd have to half it, right? So it's half of this, It's 5,050. Now, granted, I'm sure that Gauss's work didn't quite look like ours in terms of the mathematical notations and things like that. But this is the process that he went through, and it works very well, and it works very quickly. So we will take this process and alter it a little bit for some extended idea problems when we get together next time.